Okay, everybody, I'm going to attempt to explain the action potential so you guys can draw along with me. I have posted that beautiful video from Khan Academy. I think that's an excellent resource for you. I think you really should watch it because they can do things like technologically that I cannot do, all right? So what we're going to start with here is a diagram of an axon, okay? And I am following that Khan Academy video as much as I can here, all right? So here's your axon, here's your soma, all right? And what I'm going to show you are those channels, okay? So we're going to say that this here, these guys here are our sodium channels, and these on this side are our potassium channels. Okay, so that's going to make life a little bit easier for you to understand which channels I'm dealing with here. Okay, in addition to that, I'm going to be drawing sodium as pink circles. Okay, so we're going to have sodium ions, which are positive, as pink circles, and I'm going to draw potassium as a green triangle. Okay, the shapes are going to become more obvious why I had to do shapes in a little bit. So that's potassium. Okay. Now, what am I drawing again? This is an axon. And in the axon, we're going to have, in blue, we're going to have leaky channels. Okay. And I'll just draw a leaky channel in here. I really don't know the exact proportion of leaky channels to voltage gated channels. And then we're going to draw some voltage gated channels in here, okay? And we'll just draw another one. And one here, okay, and one there. All right, so we can just, if you want to, we can label this leaky channel and voltage gated, which means they're dependent on the change in voltage. Okay, so these guys are going to be sensitive to what the voltage is at the time. Voltage gated channels. Okay, and lastly, I'm going to draw over here our sodium potassium pump. All right, so on one side of the sodium potassium pump, we're going to have 3 circles, indentations, hence the circles here, okay? And on the other side of the pump, we're going to have, whoops, okay, spatially not very good. We're going to have 2 triangle indentations. Okay, just to show you that it does both. Okay, so 2 triangles, 3 circles. Okay, so catch up on that. Now, what I'm going to tell you is this. This is the whole point of this. Do we respond to a stimulus or do we not? And if we do respond, this is how the response goes. So if you're wondering what this whole action potential is it's your nervous system deciding whether it's going to send the message off that it's received. Okay, so in other words, if you were with me, now here's the best example. If you were with me in the classroom right now, if you can remember anything about room 228, there's a fan that runs in there, okay? And sometimes it's louder than others, all right? And other times. And so my example always is, okay, right now when I'm teaching this, you guys have ignored the fan because every single day you come in here and you hear it and you realize it's not of any importance. But then as soon as I draw your attention to it, you can hear it again. All right, so this really is a deciding factor as to, are we going to pay attention to the stimulus? Are we going to get a response from this stimulus? Or are we just going to ignore it? Okay, so if you're tuning things out, that means you're not going through an action potential in those particular neurons. So what we're starting with here is the resting potential, okay? And so what the heck does that resting potential mean? It means that the difference between the inside of the neuron, this is the axon, this is the neuron, this is the soma, there's our nucleus, okay? And then we would have dendrites coming out of that end. It means that the inside of the neuron is more negative than the outside, okay? And so our resting potential inside is negative 70 millivolts. So we have a difference, okay? And we maintain that potential via this sodium potassium pump. So you can, well, actually, I think I can label that. I shouldn't get too messy here. This is your sodium potassium pump. Okay, and so this maintains the negative resting potential all the time. Okay, but now let's say I open that back door in 228. This is my example I use all the time, and there's a grizzly bear there. Okay, you're going to have to respond to that. So you don't have a choice, you can't ignore it. And so what's going to happen is you're going to have, we'll say that this is the stimulus coming in. Okay, so I'm simplifying compared to Khan Academy. They are definitely more knowledgeable than I am, but I'm just going to show you that as your stimulus. All right, and so the first thing that's going to happen, I'm going to just draw something down here. I'll give you your little steps down here. Okay, yeah, you can see that. So little steps. The first thing that happens is that the sodium channels, the leaky ones, allow sodium to leak in. Okay, so we are starting at about minus 70 millivolts. Okay, and again, it could be a little different for different neurons, but that's really the standard number in that area. So we're going to go from negative 70 as these sodium channels leak in, or the sodium leaks in these leaky channels, and I will draw that for you, to about minus 55. It could be minus 50 in certain neurons, okay? So I just want you to be aware, you're going to have different sources giving you different numbers here. I've done the research on that. I'm going to stick with minus 55 today, but it could be minus 50, all right? It's not a big deal because it could be different. It is different in different neurons. So let's get to our drawing now, all right? So we've got sodium channels, and I've indicated that sodium is a circle, and sodium is in a greater concentration outside of the cell than it is inside. So two things here. Remember, your sodium is positive. Okay, so I'm drawing little positives here to indicate that, and they're all positive. So if you want to follow through and put positives beside all of those guys, that's fine. And you might have some potassium or some sodium inside. Okay, so what happens is that these leaky channels, because of this stimulus, allow sodium to leak in. Okay, and so if we're taking positives and allowing positives to come in, that's why we're changing this number here. Between negative 70 millivolts, it's going to go to about minus 55 to minus 50. All right, and that's the first step. So that basically says, and this is happening extremely quickly, okay? It's not as slow as the way I'm talking, obviously, because we'd never get anything done. You'd never hear anything. So it's going to, sodium is going to leak in. Now that's the first step. What happens once we reach this magic number, okay, is that these guys are going to start to open up. So what are they? They are sodium channels that are voltage gated. So once we reach a certain voltage that's necessary, then these guys are going to open up. Okay, now here's the thing. Why does sodium want to come in? Number one, this is what I was trying to say before, it's negative inside. So positives want to come into negatives because they're attracted, right? Opposite charges attract. Secondly, there's a concentration difference, right? So there's a lot of sodium on the outside of the neuron. There's not much sodium on the inside of the neuron, so sodium wants to come in. So two things are driving that reaction. Now, so that happens. Once we get to this magic number here, okay, it now says, okay, we're going to send this message. That grizzly bear is pretty important. So we need the brain to know, we need to react, etc. And so what happens then is your NA channels, the voltage gated channels, okay, I didn't write that down, your NA voltage gated channels, so we'll say voltage gated channels open. Okay, and so if the voltage gated channels open, now we're going to have sodium flooding in. Okay, so sodium floods in. Now the beauty of Khan Academy is that they have that ability to erase all this. Okay, and so what you're seeing here is the action potential in that trigger zone. Keep in mind what's going to happen is it's moving this way. Okay, so there are more voltage gated channels over here. And so each of them would respond. So this is a question I get when people are in front of me. Miss, how does this move down along, or does it move along? It absolutely does. The response moves from this to this to this to this, and etc. So it's moving in this direction. So eventually this one's going to work and this one's going to open too. Okay, and so the action potential moves down along this way. The response moves in this direction. And so it's going from the nucleus all the way out to the axon buds. Okay, so the terminals of the axon. All right, and then once the action potential is over here, once this whole thing has gone through its course, these guys cannot open for the refractory period, which I'm going to get to. Okay, so I'm just moving ahead, letting you know the message gets sent in this direction. How does the message get sent? It allows sodium to flood in, flood in, flood in. Okay, so that's going to be happening one after another. All right, and then once the refractory period happens, these guys cannot open up again for a very short period of time. And that makes sure that everything moves in this direction. Okay, so we're at the point where Na channels are open. Sodium is flooding in. Okay, at this point, we're going to reach about, we're getting very positive, okay, and we're going to reach about a positive 50 millivolt charge, okay. So in other words, we've gone from negative 70 to positive 50 or so. At that point, what happens is the sodium channels close. Okay, so they're saying the message is going forward, it's been sent, and we're going to close. These guys are closing on this side. Okay, and so again, this will be open for a short period of time, then it'll close, and there'll be more voltage gated channels, and they'll close as well. All right, so now we've got lots and lots of positive inside, and then we have negatives, or we want to restore this. Okay, so the ultimate goal of the action potential is send this chemical, electrical message down the axon, and then we want to restore this so that the message goes only in one direction and this neuron is no longer firing for a short period of time. And so what happens then is the potassium channels that we haven't talked about open up. So now we're going to draw some potassium in here, okay? And so we've got potassium inside the neuron, and I'll show you in a few minutes how that gets there. And of course, there's some potassium outside of the neuron. Okay, and so what happens now is the potassium channels open up. They're always a little bit leaky, okay? So there are always these little leaky channels that are allowing potassium to leave. But now the voltage-gated channels are going to open. And the voltage-gated channels allow potassium to leave. Now, what charge is potassium carrying with it? Potassium is also positive. So we've gone from minus 70 to positive 50, and now as soon as we allow these guys to exit, we're not allowing any more positives to come in, and we're allowing positives to exit, you can foresee that this number, the positive 50, is going to get more and more negative, okay? And that's the goal, because we want to restore minus 70. So these guys are open, and because there's so much positive charge in there, the positive charge is repelled outside of that neuron, okay? So we're going to get that working. And that's going to help to maintain or to restore our negative action potential. Okay, so we're at positive 50, this closes, and then a couple things happen. Okay, so we've got the potassium channels opening. Sorry, I'm writing on a slant here, unfortunately. And now here is something else I have to tell you. Whoops. I should say sodium potassium because that is what it's called. The sodium potassium pump turns on. Okay? Now, the sodium potassium pump turns on, and this is what it does. So notice there are 3 spots for sodium. This will close up. Okay, if you can imagine these guys are together. This closes up, and what does it do? It transports 3 Na out. So 3 potassiums are going to exit. What is that going to do? It's going to restore negative potential, okay? But what it also does is, so if you can imagine, that's going to happen first. So we're going to get 3 potassium exiting. So 3 potassiums are going to leave. Go, 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 okay? And then what it does is it brings in, did I say potassium? 3 sodiums are going to leave. And then 2 potassiums are brought in. Potassium ions are brought in, okay? So every time the sodium potassium pump works, it takes 3 negative charges out and brings it takes 3 positive charges out and brings 2 positive charges in. So you can imagine, because of that differential, you're going to get a negative charge inside. 3 positives, subtract 2 positives is only going to leave you with 1 positive, okay? But you're getting a whole extra positive outside of the membrane, and that's going to help restore this as well. So you've got the sodium potassium pump turning on. All right. This, by the way, uses tons and tons of ATP. Just an aside there, something I would normally tell my students. And then eventually the potassium channels close. And then we have our negative potential restored. Okay. This is called the refractory period at this point. What that means is nothing can fire that's already fired. Okay. It's on a break, and the action potential is moving in this direction. So we would have other channels over here working, okay, going through this process exactly, and then sending the message to the axon, which will send it to the dendrite of the next neuron. I hope that helped.